like the theta naught and theta 1 which we are having. Like say, like if we summarize first part, the first part is related to your what is the machine learning algorithm. And in the machine learning algorithm, we have covered different types of learning. Next, we have seen your supervised learning. And in supervised learning, basically, we have covered your classification and regression. And regression, we are basically we are covering this regression in more detail. So in your regression, we have seen how we can create the model. See, so basically here in this case, in case of your regression, we are basically trying to formulate your function, and that function is basically going to help you to uh, um, basically map your input to your output. So that is the case. Means we are going to just apply your x, and this x is going to be mapped into your y, and that y in case of a regression is going to be a continuous value. So now next important thing which we have seen, what the kind of the effect these thetas are going to play. How based upon the selection of your theta, the placement of the line is going to be different. And now how based upon the placement of your line at the different location, how the cost function is going to be affected. So the selection of your different thetas, it's really going to affect your the placement of the line, and that is going to affect your cost function which are associated with it. Okay, now next point which we have seen is related to your the deriving the value of your theta. So one of the way we have seen the basically in that case we have seen how we can select the value of your theta, right? So now next we are going to first, before moving to the further detail, first we will see how we can use how we can prepare this model. So that we are going to see practically, we are going to explore it, how we can prepare the model and how we can use that model for the for your future prediction, how we can use it. So that part we are going to explore next. Okay, so everyone can open the this collab. So here I'm sharing my screen. So hopefully it is visible to everyone. So now what we are going to see is we are going to see how we can use this regression algorithm to, means how based upon the regression algorithm, how we can prepare the model and how we can use it for the classification. Okay. So now first thing which we are going to see is, first we will see the example which we have covered in your class, in your theory class. So first let's see what value we are going to get for your thetas, right? So let's see for your the considered problem. So first, before that, I will be importing some of the libraries. So this thing you have already covered in your Python class. So first, I'm just going to import some of the important library. I'm just, so you can also start at your end. So we will be just going through these some of the ways. First, we will be exploring these libraries, and then we will go with the detail. So here what I have done is I have just imported some of the libraries. So this is for now. This is like we can, okay, let it be. So these are the libraries which we have imported. Now next what we are going to do is we are going to supply your input. So the case which we have covered, in that particular case we were having some 5 values we were having. So I'm going to feed these values first. So these values are were you 2, 3, 5, 7, and 9. X, this is your X, that means your input which you are going to supply. And next which we are going to write, that is related to your class level. So this is going to be your, this is going to be for your class 4, 5, 7, 10, 15. You should just feed it into your proper way. So we will be using this. So 5, 1. So these are your input. Okay. So let's see. First, let's connect it and then run it. This is just to see what is the shape of my input. So all of you can also start writing this code. So for now, what we are going to do is we are just going to supply your input. So here we have just supplied your input, and the shape of your input is the 5, just one column we are having, right? So we are having 5 entries, and this entries are having just one dimension. Means 5 features, 5 instances we are having, and these instances have been described with respect to the one feature. Like in the case where we were having the number of hours of sunshine, and based upon that you were having the ice cream selling, right? So this is representing the hours of sunshine, and this is representing your ice cream sold, right? Now, next what we are going to do is we are basically going to initialize your model, right? So for that only we have imported this. We are going to use this regression model, linear regression model, and that is present here in the SK. So we have imported this. Now, next we are going to do the model initialization. So we are going to do the model. Model initialization we are going to do is, so suppose here I'm referring it as the egg, and this is your linear regression. So now we have initialized your model. Next, what we are going to do is we are going to fit your model. So the things which we have covered related to your deriving the value of your coefficient, that is your theta naught and theta 1. So that is going to be take place in that particular steps are going to take place in this after writing this one. So here what we are going to do is we are going to fit your model. We are going to fit the data, or we are going to fit the model. So here what we are going to write. So this is your regression model. This regression model, we are going to fit it on your x, y. That is your input and means input instances and your class instances. Okay. So now here we have fitted your model. Okay. So if you want to check it, what is the value of your intercept and your this slope? So that also you can check it. So like suppose for the slope, I will be writing with dots coefficient. And for your for your intercept, I will be using regression dot intercept. So this is just going to show you what is the value of your slope and intercept, the theta naught and theta 1, which we were talking about. So this you could see by fitting your model on your training. So all the mathematical calculation which we have done, that is behind the scene which is working, right? So now once you are done with the model building process, so this is your model. In your model, we will be requiring the value of your theta naught and theta 1. So that we have calculated. Now, once you are having the model, we can use it for the prediction. So for the prediction, either you can go with the manual calculation also, and if you wish, you can also calculate it using function also you can calculate. So let's first see using the using a manual calculation. So here I'm writing print. In your print, what I'm going to write, first one is the theta naught plus theta 1 is. Theta naught, that means this part. This is your theta naught. theta naught plus theta 1, that is your theta 1, that is your theta 1, theta naught and theta 1, and suppose the value, like in that particular case we have taken 8, means for if the number if the sunshine is 8 hours, then what will be the selling for your selling for your ice cream? So that we need to predict it. So that we have predicted it as in the 12.45. Hopefully that you are able to recall it. So like you could see here, we are also getting the same result. Okay, so either you can do it in this way, or you can also calculate it, means using the function also you can calculate. So suppose if you want to calculate it based upon the function, so what you will be doing, regression, that is your model. Then we will be using this predict. Predict we will be using in order to do the prediction of your input, which you are going to supply. So here we will be supplying your value, that is your entry array. So it's going to be 8. So like you could see, we are getting the same result. So here I'm repeating this whole part again. So first what we have done is, for now it is means we are not plotting anything, so it's not required. So first we have created your NumPy array. We have supplied your input in your NumPy array. Next we have initialized your model. We have fitted your model on your X and Y. Now, once you are able to fit your model, so that means fitting of your model, that means we are able to derive the value of your slope and intercept. Once you are able to derive the value of your slope and intercept, we are able to calculate, we will be able to use it for your prediction. So like here, first we have done the manual calculation, and next we are predicting the value using your function. So in both the cases, you are going to get the same answer. Okay. So that way means if you wish, you can supply your input, means you can manually enter your values, and based upon that you can use, means based upon that manually entered value, you can basically you can create your regression model, and you can use it for the means you can use it for the prediction. Now, yes, we will be doing it. Just wait for a second. I'm going to come to that point. Graph plotting also, where you will see you are having a line, and on around the line you are having the plots. That we will see. Just wait for me. So this is just to explain you the example which we have covered. This is also the same way. It means here also we are able to derive the same. Coming to the another part, like suppose here what we have done is we have calculated your means we have manually entered your value. Suppose if you wish to enter the value, you are having a file. In that file you are having the value, and from that file basically you would like to, for that supplied input, you would like to create the model. So there are different ways to basically give your input. So here I'm going to explain one of the way. So here what I'm going to do is I am going to supply, just a second. So here I'm going to upload one of my file. So here I'm going to upload it. So you can basically download it from a supplied URL. You can also place your file in your drive, and from that drive also you can extract it. And this is the another way where I am basically in this particular workspace only. I am going to upload it and I am going to use it. So this is one of the simplistic way to upload your file and do all kinds of the experiments. So here what the data set is, let's first see what this data set is. So in this particular data set, we are having the two information. The first information is related to hours of study, And the next information is related to your test score. So the number of hours of study you are doing, based upon that you are going to have the test score. Okay, so this is the data set, and for that data set we are going to we are going to prepare the model. So here you are having your prediction in terms of the numerical value, and you would like to predict you would like to prepare a model, and that model basically going to help you to predict the test score based upon your supplied accounts. Okay, so let's see how it is going to work. So first, what we are going to do is we are going to read the input. Okay, so in order to read the input, like this is your CSV file, right? So in order to read your CSV file, I will be using my this with your Panda. I will be doing that. So let's first import the Panda. Import Panda SPG. Let's import your matplot. Here we will be doing some plotting also. Matplotlib dot pyplot SPLP. Now next we are going to read your CSV file. So in order to read your CSV file, I am going to use pd dot read CSV. Here I'm going to supply the name of my file. So name of the file is grade set underscore one dot CSV. Also test it whether you are able to read it or not, and what kind of information is present, so that also you can test it. So here just going to display whether you are able to, okay, saying there is no file. Okay, we were having small and capital keys. That's it. So now you could see here it is showing the hours of study, and it is also showing the test grade. Okay. Now next what we are going to do is we are going to first read it in terms of your X and Y. So first here I'm going to read it in terms of your X. X is going to be your input. So here so I'm just going to copy it. So there will be no. So here it's just I'm reading this part. So all those I'm going to read it, and then we dot new X next Y is going to dx dot test grade. This let's test it whether we are able to read it or not. Yes, we are able to read it. Now next let's see. The first thing is what we are going to do is we are going to call your, like once you are able to read it, right? These steps we have just done to perform the reading in your X and Y. Now next step what we have done is we have prepared your initialize your model. Next we have fitted your model. So I am going to use this same set of line in order to prepare our model, because there is no change. So that's why I'm simply copying it. So X and Y, in your X and Y only I have read it. So now you could see we are getting this slope and we are getting this intercept. Okay. So if you wish, you can supply your input, and based upon that input, it is you can do your prediction. So like suppose here I'm going to do my prediction. So I'm just going to supply one of the inputs. So suppose the input is predict. Suppose input is 6, for example. If I'm learning for 6 hours, then my score will be 17. Okay. Now let's see it in a visual terms also, right? So now next what we are, hopefully all of you are able to get it. Yes, I missed it. That one. Yes. Okay. So let's see how we can do this plot. So for plotting, we are going to do the scatter plot. So a scatter plot we will be doing between your x and y. Next, what we are going to do is we are going to draw that line, right? So in order to draw that line, basically this line has been drawn based upon your calculated value of your this theta naught and theta 1. And this we can easily, either you can use this manual calculation or you can also use this predictive function to basically draw that value. So here I'm going to use this function to draw that value. So here it's your x, that is your basically the number of hours. For your y, that means your predicted value. I am going to use this function predict, and here I am going to supply this x, because based upon the x only you are going to have the prediction, right? So now this will be the case. You could see, okay, let me change the color. So you could see these all are your values, and this is your prediction which we were talking about, the line, the model which we were talking about. This line is your model. Yes. So yes, everyone is able to get it till this point. Can we move further? Yes. So now this means hopefully all of you are able to relate how we can use these, means how we can basically practically implement your regression model, how we can use this Python to implement to create your model using your regression. Okay. Now next part, again we are going to come back to your theory part, and then we will see this we will resume this practical session. So first I am going to cover the another important part that is related to your how to quantify how good my model is. So next first we are going to see this part, okay, and then we will come back to your practical. So this iterative adjustment that we will see for now, first I'm going to cover all the elementary part, and then we will come back to your the iterative adjustment of your key. So now in case of like we have learned how we can create the model. Even we have learned how to implement your model. Next important point which we are going to see is how to quantify. Is there any other way to quantify how good my model is? So like the performance measure which we have discussed in case of your classification, like the accuracy thing which we were talking. So in case of the accuracy, basically it is quantifying how much correct prediction we were able to do. So in case of the regression, instead of using accuracy, we are having some other ways to quantify how good my model is, how good it is, basically it is behaving. So one of the measure is your R square measure. So basically this R square measure is also referred as the coefficient of determination. It is referring, or it is basically showing how close your model is able to fit, how close your each of the points of your training instances is able to fit to the regression line which you have drawn. So that we are going to see, or that we are going to quantify using your R square measure. Again, repeating this part, R square basically it is going to measure how close your data points are to your regression line. So that we are going to quantify using your regression, this R square. The good value for it means the value for your R square, it should be between 0 to 1. The 1, if it is close to 1, or if it is 1, then it is a perfect 1, and if it is a near to 0, then it is it means some more modification needs to be done in order to make it as in the correct one. That means your model is not basically representing your training instances very well, or the instances very well. It is not able to hold the information. It is not able to present the information. So that we can quantify using your R square. Now, how we can calculate this R square? So this R square could be calculated based upon your, here in this case, we will be using the information of your the regression. We will be using the information of your how better your model is from the mean representation. Now, what is the meaning of it? So, like suppose if you want to present your data. So, whenever we are talking about the presentation of your data, means just one value to present your data. So, the simplistic way is your mean. I can use mean to present my data. I mean, I can use mean as in the representative of my data. So, here, here in case of your regression, we can also have a mean line. Sorry. We can also have a mean line which we could use it for the representation. But we are not using this mean. We are basically having some another line which we are saying it as in the representative of my training instances, and that we are using it as my model. So here this R square is basically going to quantify, is there any means basically what the thing is there any other way other than your mean where with which I can represent my data very well. So that we are basically trying to do in a regression. Is there any other way better than this mean line? Okay, so for that we are basically going to use this R square. So this R square, as I said, it is going to be based upon your regression. So the formula is going to be 1 minus sum of square regression error divided by sum of square total error. If the difference between your actual value and the predicted value is less, that means it is this part is going to be very small. If the actual value, if the difference between the actual value and the predicted value is less, so in that case, this part is going to be near to 0. If it is near to 0, this whole part is going to be very small and the value is going to be more close to 1. But if the difference is very large, so in that case, this is going to be more, it's going to move towards the minus, or even it's going to move towards the 0, even it's going beyond. Means it could be your -1, right? Because this value is very large. The difference between your actual and the predicted is large. So this is going to be large. And if this is large, so this pole is going to be moved towards 0, or even it can go below than 0 also. Okay, so that way this R square is going to help us to quantify how good your model is. Okay, so now how these values are going to be computed. So this sum of square total is going to be computed based upon the difference of your mean and your actual value. This is the summation of your difference between the actual value and the mean value. So that is going to be sum of square total. So like you could see, this is the actual value and this is the mean value. So sum of square total is going to be difference between the actual and the mean. Coming to sum of square regression. So sum of square regression is going to be the difference of your predicted value and the actual. So sum of square regression, it's going to be the difference of your actual value and the predicted value. So this way you will be able to calculate this, means you are able to calculate the sum of square regression and sum of square total. Just place all your values here. You are going to get your R square. This part I have just explained you when the value is means when there is no difference. So this part is going to be very small or near to 0. When it is near to 0, this part means you are going to get the R square as in 1. Okay. So now let's see with an example how it's going to be. Let's see this part. So this is very small, in a very elementary way, these things has been written so that you can figure it out what exactly calculation we were doing. Okay. So now the first sum of square total was based upon the squaring of the difference between the actual and the mean. So like you could see, the mean value is this one. Okay, so it's going to be the difference between the actual value and the mean. So this all are the difference between the actual, that means this part, and this 1 minus this 13 and the squaring of that. Although you can write it in directly, but yes, just to explain each and every step in a very minute way. So that's why I have written this. Okay. So this will be the case. So here, what we have done is we have just calculated the difference of your actual and the mean, and then we were doing these squares. So this is going to be sum of square total, which is the summation of all this. Okay. Now coming to sum of square regression. So in case of a sum of square regression, first thing is, first I need to calculate my predicted value. In order to calculate my predicted value, the formula is with 6x minus 5. So first I will calculate these 6x minus 5, where x is going to be 0, 1, 2, 3, 4, 5, 6. So this is your predicted value. These all are your predicted value. Next, what we are going to do is we will be calculating the difference of your actual and predicted. So here you could see this is the difference between the actual, this is the actual and the predicted. And then we are doing the square of it. So this whole value is going to be based upon your actual difference between the actual and the predicted. Now next step was doing the squaring of it. So here we have done the square. So this whole calculation is going to lead to your sum of square regression. Now we have calculated sum of square total also and sum of square regression also. So this is going to be 1 minus sum of square regression and sum of square total. So what value we are getting? We are getting it as a 0.92, which is quite close towards your. So that is basically it is close toward 1. So that means we are able to represent our data variable. Not exactly, but yes, we are able to represent our data variable. Okay, so that way it's that way you can use R square for the quantifying how good your. Okay, now let's see all these cases. This R square with respect to your means how we can use it here. So like till this point, it is hopefully till this point it is clear to everyone how we are feeding your data and then how we are calculating. Okay. Now here either you can go with the manual calculation for the R square or you can use some inbuilt function. So for the inbuilt function you are having this means you need to import it. So here I'm going to import it from your sklearn. So from sklearn dot metrics import R2 store. So this is the way with which we can import your R2 score. Now once we have imported your R2 score, I can use it for calculating my value. So here I'm going to write it. So here I'm writing print. So now here in this case, what you need to supply? You needed to supply your actual. The input here in this case, the input is going to be your actual. Actual and your actual, that means your true class label and your predicted class label. So here we haven't predicted this. We haven't done the prediction on your X. So first what we are going to do is we are going to do the prediction on X. So either you can supply, either you can have some variable, on that variable you can supply the input, or you can do it here also. So regression dot predict, and in that I'm going to supply my X, because on X only you are going to do the prediction. So let's see what output we are going to get. Yes, you could see what we are getting, 97.5. One more thing is, like suppose this you wanted to know how it should be written, or so let's search it also. So it's going to be sklearn R2. So you can just refer these documentation in order to get it more about this R2 score. So for now, I'm not exploring the other option. I will be just using the basic one. So you could see here, this is the basic. You needed to supply your true class label. You needed to supply your predicted class label. And based upon that, it is going to do the prediction. Okay, so that you can import it and you can use it. So here, simply what we have done is, we have imported this library. We have imported. Next, what we have done is we have called this function. In this called function, I have supplied my I have supplied my actual class label and I have supplied my predicted class label. And based upon that, it is going to calculate the R square. Okay. So yes, hopefully all of you are doing along with me this calculation or this whole practical thing. All of you are doing. Yes. Okay, let me know if any of the point is not clear. I will repeat it again. Now, next coming to the point, like one of the measure is your R square. Now, there are other measures also, like the root mean square is also there. Mean absolute error is also there. So let's see. Okay, let me write it here. So there are, and for all these, the function which I'm explaining, so for all these functions, means for all these measures, the functions are available so that you can also directly code. So the one of the measure is your root mean square error. So root mean square error, basically the formula is just a formula. So here it's going to 1 divided by n. That is going to be the number of the instances which you are having. And you need to perform the summation over I is equals to 1 to n. And here also you will be doing you are going to calculate the difference between the actual and the predicted. So this is going to be a root mean square error. Okay. There is another measure also that is based upon the mean absolute error. So that is also referred as a MAE, mean absolute error. So it's just the absolute difference between the actual and the predicted. So it's going to be I is equals to 1 to n, and here you will be doing you are going to calculate the difference between the actual and the predicted one. It's just the absolute difference between the actual and the predicted one. So that is the case. So these are your 3 different ways. There are other ways also to quantify. Here I'm just mentioning 3 of them. The one is your R square. Next one is the mean absolute difference. And the another one is your root mean square. In all the cases, you could see, in all the cases, we are using the actual and the predicted one. Some or the other way, we were using actual and predicted one to quantify how my model is going to work for my supply days. Okay, now let's see how these value could also be calculated. So for these value also we are having direct function is there so that we can call it. So here I'm going to mention it. So the first one is for root mean square. Next one is your mean, that we are referring it as in the MAE, mean absolute error. Next one is your mean squared. So first you need to import all these. First you need to import root mean absolute error, this mean squared error. Now next we are going to use it for our task. So let's see how. So the first what we are going to calculate is we are going to calculate the mean absolute error. So for mean absolute error again, I need to first call this function mean absolute error. In this, I will be supplying my y and the predicted. So the same thing I need to supply. So this thing has to be supplied, that we needed to supply here. Okay. Now next come is your root mean square error. So root mean square, root mean square error. So for this, we are not having the direct function. We are having this mean square error. So that we are going to calculate its square root. Square root of your mean. Now this is the value for your root sorry, not for your r square, mean absolute error, and root mean squared. Okay, so these are the way with which you can quantify. There are other measures also, like the adjusted r square is also there, which could be used to quantify how good your model. Okay, so hopefully till this part also it is clear to everyone how we could quantify how good my model is. Now moving to the another important part which has been asked in during this session, like suppose if the structure of your, like if your data is complex in nature, like it is not having all the time, it is not required, like you are having the linear relationship, it could be a non-linear also. Then in that case, how to go about? Because if you're trying to fit the linear model in the non-linear data, so in that case the performance is not going to be good. Like what the case is, like suppose one of the case which we have seen, like suppose here I'm going to draw it. So like suppose if the structure of data is like this, you can fit this straight line in order to basically represent all these instances. Means your model could be in this way. But if the value is somewhat like this, it is not going to be, if you're just going to fit this straight line, so this is not going to be a good representation of your model. There should be somewhat like this kind of some curved structure should be there in order to cover that non-linear, and that is not possible with a simple linear relation. So in order, when the data is non-linear in nature, so for that case, instead of fitting the linear model, we need to go with the non-linear. Okay, that is basically covered in case of your polynomial regression. So like you could see here, like this is the structure. Like this is the structure of your data. Means like this, it is not just a straight relationship it is holding. In your x and y, we are not having a linear relationship. Here we are having some curved structure is there. So when this is the case, you could see as you have tried to fit your linear model, what r square I'm getting. I'm getting this r square is in 0.1, which is very less. The value should be near to 1, but we are getting the value near to 0. Not exactly 0, but yes, near to 0. So instead of having this straight line, if I can make it somewhat curved, so I will be able to hold the information which is present in my training instances. If I'm able to do it, I will be able to reduce the gap. And I will also be able to make the better prediction for my test instances. So now you could see here that for the same data set, the performance, the R square has improved from 0.18 to 0.9. And why is it the case? Just I have made this correction. So at the complicated information, the complex information which was present in my data, that I have tried to incorporate in my, and because of that, my model is able to perform comparatively better than the previous. Okay. Now the grade, basically here I have covered the grade. So for the grade, like suppose this is your data, right? So in this data, how much you getting? We are getting 97%. Okay. Now here in this data itself, what we have done is, yes, somewhat we have modified some of the instances. Now these part, like in this case, near about this is holding somewhat linear relationship. But now here in this case, it is not holding a linear relationship. Some curved, it is some complicated information is there, which was not basically taken care by this part, right? Now here in this case also, In these two parts, it is not holding a linear relationship. But what we have done, we have tried to formulate it using a linear relationship. So earlier it was your 0.97. That because of this missing part, it has reduced to 0.9. Although not much in decrement, but yes, it is a small data set, and because some very small changes has been done, and because of that very small changes, a little bit of decrement we are able to observe in your arts. So now here you could see, now from your 9.5, as we are going to make it some curved one, it has improved from 0.95 to 0.96. So in all the cases, what we are trying to do is basically we are trying to model the relationship between X and Y, and that too in terms of your nth degree. So earlier, what was the case? Earlier we were having this. Now we have added this loop in order to cover this non-linearity. It is not the case always this kind of means when you are going to model in this way, then only it is going to fulfill, or it's going to achieve the objective which you would like to. It could be a different also, like basically a case like suppose cover this one. Like here in this case, it is covering this part. In the another case, it might be a case you need to model in this. So it is not the case all the time you have to model in terms of this part. That you have to figure it out which of the case, in what way you will be able to fit it. That is going to be your experimental part. Okay. So hopefully this part it is clear why there is a requirement of modeling the modeling your X and Y in your polynomials. Okay. Now here these all are going to be, this is basically going to be your X. That means it's going to be your input, it's going to be your feature. And these all are the parameters are going to be associated with the features. One more important point is the number of your parameters is going to depend upon how many features you are having. Suppose the number of feature is 1, so in that case the parameter is going to be 2. When the feature is 5, then in that case the number of parameters is going to be 6. So all the time the number of the parameters are going to be +1, because theta naught we were having, and rest of the parameters are going to be associated with your features. Now here in this case, although we were having this one parameter, but because of the because of introducing this polynomial thing in your model, now the number of the parameters are going to increase by 1. Like I have just modeled it X, and next I have modeled it as an X square. So just one dimension I have increased. So because of that, the number of the parameters are going to be there. So first one is your theta naught, next one is your theta 1 going to be associated with your X. Next is going to be theta 2, which is going to be associated with your X square. So the number of the polynomial, form which you are going to introduce in your equation, with respect to that, the number of the parameters are also going to increase. Okay. So now these all are representing your different case. So here the polynomial degree is 3, where here the polynomial degree is 7, here the polynomial degree is 10. So now you could see from your this number, it is increasing, or it is basically moving towards your 1. So basically by increasing the complexity of the model, we are basically trying to exactly fit with your model, fit with your training instances. So as we are trying to fit with your training instances, so the R square value is also going to increase in that proportion. So like here you could see, it is exactly like it is touching each and every instance. A little bit of difference is there, but yes, still it is able to touch it. Here in this case also little bit of difference is there, but still it is able to touch it. But you could see for most of the cases, it is able to touch it by drawn bound. Okay. So that way this polynomial regression is going to help you to basically model the it's able to basically model the complex information which is present in the data. Okay. Now this polynomial regression could also be represented in a linear equation form. How is it the case? Like in case of a linear equation, how we were modeling it, theta naught plus theta 1x plus theta 2x. Like that way we were modeling, right? So like suppose to x1 and x2. Internally, this x1 and x2 could be in this way, but in from your uh, external point, it is looking like a linear. But internally it's your in this. Now, one important point is here I have explained like you are modeling in terms of the square or any power you are modeling. But this is not going to be the case always. There might be a requirement where you have to use another function to basically cover the complex information which is present in your data. So this b1 dot b2 dot basically it is representing you different kind of the function which you could include in your model in order to basically draw or in order to basically retain or extract the information which is present in the data. So these could be your same, these could be or different also. Like the case here, instead of modeling in a square, it has been modeled in terms of your square. Okay, so this is your polynomial regression. So let's see how this polynomial regression we could use it or we can implement. So now, like in case of your linear regression, we were having a direct function, and with respect to that direct function, we were creating your model. And now, once we are done with the creation of the model, we are using it for the your prediction also. So now, for the polynomial regression, also we are having the direct function that we can use. Okay. So here I am going to first import that function. sklearn dot I will explain why it is come under in your pre-processing. Okay, so data set we have already. Okay, let me first do it with your data set. So this we have done with your data set 1. Now let's do it with the first data set 2. Little bit of change has been done here. So I'm just running it. I have just changed the name of your data set, nothing else. Okay, so like you could see the behavior which I was showing there. So now you could see here it is your some kind of curved. Here also this is different from your linear one. And what value we are getting? We are getting it as 0.95. In earlier case, we were getting this as 0.97, I think. Okay, now let's do it using your polynomial. So when we are going to do it is in polynomial. So first what we are going to do is we are going to first transform your input. Means we are basically going to transform your input into the nth power, into the polynomial form, and then we are going to fit the mode. So for that we are going to use poly FEA, means any name you can take it. So polynomial feature. Here you need to specify the degree. So for now I am going to specify the degree as in 2. Next I am going to model it. So I will be fitting it. Fit transform. I'm going to supply this X. So we were having 13 instances. Now let's test it for this one. Now you could see instead of 1, you could see now it has been transformed into the nth power, and because of that, instead of seeing just 1 dimension, you are able to see the 3 dimensions. Let's increase it further. Like you could see, now you are able to see the 11 dimension. So it is going to increase with respect to the what degree you are seeing. Based upon that, it is going to increase. Okay. So let's come down to your, like, what we have done is we have just transformed your model. Now, once you are able to not the model, you have transformed your input. Okay. Now, once you are able to transform the model, we are going to transform your input. We are going to fit it on your linear model. So this is just the transformation part. Next, we are going to fit it on this model only. So I'm just to save the time, I'm going to copy this whole thing. I'm going to copy this one. So now instead of the X, it is your X. Sorry. X has one feature, but linear is expecting 11. Linear regression, just let me convince. There is no problem with this. Okay. Okay, this now you could see these are your slope. That means theta 1, theta 2 till your theta 11, and this is your intercept. Now let's calculate your mean square, also r square, mean absolute error, and root mean square. So here again I'm going to copy it. Y, where is get predicted? I need to write, okay, X poly.
X and Y has to be X on top scatter.
Now you could see what r square you were getting. You were getting r square as a 0.95 in your earlier case. Now it has been improved to your 0.999. So that way this polynomial form is going to work. Like here in this case, what we were getting 0.95, and mean square and root mean square, that also was quite large. Here in this case, these has been reduced. All three values has been have been reduced. Okay, so that way, if the data is complex in nature, we can use this polynomial form to model the relationship, to model this nonlinear. Okay. Now coming to the another part of it, like suppose here in this case, whatever things we have covered. So these things we have covered with respect to your, we were just having the one feature. And with respect to that, we have seen your simple and we have seen with this, these linear, polynomial also. But most of the cases, it is going to be you are having, instead of having just one feature, we are going to have multiple features. So multiple features, that means it is going to be a multiple linear regression. So in case of a multiple linear regression, instead of having just one dimension, you are going to have the multiple dimension. Like if you take the example of your house only. So in case of a house, the size of your house, that was the case. The area, the number of the bedroom, number of the balcony, the location of your house. These are also going to help you to basically explain the properties of your house. So when you will be using all these information, the modeling or the predicting of your price of the house is going to be more accurate, right? So if it is just simple linear regression, if it is a one feature, then it is a simple linear regression. And if it is a multiple feature, so in that case, it is going to be a multiple linear regression. And now the rest of the things which we have covered with respect to your simple linear regression, that is going to be the same for the multiple also. The only difference is going to be the number of the features. In your earlier case, we were just considering the one feature. Now here in this case, the number of features are going to be more than your one it's going to be. Okay. So let's see your multiple. Like this part we have just we have covered till this point. We were having just the size of your house, and based upon the size of the house, we were predicting the price of the house. That was the case. Now here, instead of having just one, we can basically add on the multiple dimension too. So here the multiple dimension could be bathroom or any other features could also be there, and those features you can use it in order to prepare you. So it is going to be the same way as we have worked till this point. The way we were using this linear regression or the polynomial, the same way it is also going to work. But the number of the coefficient, which in your simple linear regression, the number of the coefficient was just 2, as we were having just one feature. But in case of your multiple one, it is going to increase with the number of the dimension which we have added. Like if we talk about this one, so here the number of dimension is 2, so the coefficient are going to be 3, theta naught, theta 1, and your theta. And this way your line is going to fit, and based upon that line, now the line based upon this plane, you are going to quantify, or you are going to calculate what will be the price of the house. Okay, so these are the some of the possible input which you could have for your house price prediction problem. Means to describe your houses, the size, the bedroom, location, number of balcony, number of bathroom, year when it was built, and the number of floor. You can also include the other dimensions also. Here I have listed some of them. So now the general notation for this multiple linear regression, the y is going to be the same, the way we have covered. So here you're just going to have the one y, and that is going to be associated with respect to each of your instances. Like in case of a simple, or in case of a single linear regression also, you are having the x, you are having the y, so that will be the case in this case also. But instead of having just one feature, here it is going to be multiple features. So the notation for your multiple linear regression, or this where you will be using the multiple linear regression, it is going to be represented in this xij. That means it is representing your ith instance and jth feature, because the dimension, this dimension has been now it's going to be more than. Now the dimension is going to be more than. So the formulation, the representation of the instance is going to be xi, that means your ith instance, and jth dimension. Okay. This is just the notation part of it, how you will be representing your input. In the earlier case, what we were having is we were having this notation, like we would, if you would like to present your predicted value. So the predicted value was that in that case, it's like this is the representation. So it was your theta naught plus theta 1x plus this error term. That was the case when we were working with your simple linear regression. In case of your multiple linear regression, the same thing has been written in this way. So it's going to be like, it's going to be in this way. yi is equals to theta naught plus theta 1 x1. This is with respect to your first instance, first feature. Same you will be having with respect to your first instance, second feature. Same you will be having with respect to your first instance and your third feature. That way it's going to be the representation. Now here it has been written in blue. Why is it the case? Because like you were having this theta naught, okay, theta naught, theta 1, theta 2 and theta 3. And with respect to each, we are having associated x. But in order to write it in this way, this theta naught is not having any x. So how or why I can write it, why I need to write it in this way? Just to summarize it, just to represent in a common format, the assumption or the value which has been taken as an x theta x naught, and the value of x naught is taken as in 1. So whether to write it, it is in the theta naught, or whether to write it as in theta naught x naught, where the x naught is equals to 1, both are going to be same. It's not going to make any difference. Just to simplify it in this way, the value of your x naught, the x naught has been taken, and the value of this x naught is always going to be 1. So that it could be represented in this way. Hopefully all of you are getting this concept. So what means how we are able to write it, this theta naught and theta 1x in this way. Here we have just associated this x naught, and the value of the x naught all the time it's going to be 1. Like you could see, the value of your first feature is always going to be 1. For rest of the it is going to be different, but for the first feature it is always it's going to be 1. So whether to write it in your theta or whether to write it in theta naught and x1, it is not going to make any difference. Yes, there is a question related to if you are going to increase the polynomial degree. Yes, if you are going to increase the polynomial degree, basically means for one point of the time it is going to provide the advantage, but after that peak it is going to basically behave as in the disadvantage. How is it the case? Like suppose what I am trying to do with respect to your increasing degree of polynomial, if you are increasing the polynomials, right? So basically what you are trying to do is you are trying to fit with your training instances. You are trying to make a more complex model. So when you are going to make a more complex model, it is going to be the case, it is going to work well for your training instances, but it is not going to work for your test instances. So basically the relation between your model complexity and your performance is going to be like this. Like suppose this is your model complexity, and this is suppose your error part or performance part, right? So when your model is very simple, it might be a case for your training instances, for training you are having very large error. But as you are going to increase the model complexity, your error is going to reduce for your training instances. That will be the case. But for the other case, what our objective? Our objective is our model should work good for your test instances. So yes, when you are going to increase the complexity of your model, for some point it is going to decrease, but after some point it is going to increase. because your model has fitted to your training instances so well that it is not able to work. It is not able to work in a very good way for your test instances. So that will be the case. So if you are increasing the polynomial, so possibly it is the model is going to fit, or it is going to cover each and every aspect or each and every detail of the training instances. But yes, that might be a case. It is not going to work for your test instance. Okay. So yes, is it clear? So that is the case. This is just to simplify it. This assumption has been taken. X naught is going to be 1. So the same thing, the modeling thing means again, it is not the case you are having the n number of the features, you can't go with the polynomial. So that experiment you can also try in this case also. Okay. So this is just a simple linear regression. If you are doing the that part we have covered, the intercept and the slope one. If you are basically the slope is defining if I am changing the size of my house with a 1 square foot, how much change I will have in my price of my home. So this way you can analyze the effect of this particular part, In case of your multiple features, if you want to analyze the effect of a particular feature, so what you can do is you can fix one, like here in this case, you can fix this one and you can vary with you. You can do the analysis with respect to this. So that way you will be able to analyze the effect of the other feature, like the way we were doing here. The same way you can do it for your multiple features. So that way you can do the analysis. Okay. Now coming to the another part of it, like this is the same thing which we have just covered. So this is your theta naught, theta 1, theta 2. You are having x naught, x1, x2, x3. Just to make it this one. So what has been done? It has been transformed. So it is going to be theta naught, theta 1, theta 2 that way. And here you are having the x naught, x1 and your x3. So it's just the transformation of your theta naught into x. So now your whole model, like in your previous case, in case of a simple linear regression, the case was your h theta x was written as in theta naught plus theta 1x. Here in this case, it is going to be written as in a theta transpose x. Now your model is going to look like theta transpose in case of your multiple. Now, as we have changed your hypothesis, as we have changed your model, so with respect to that, you are also going to have change in your parameter. You are also going to have change in your cost function. So in case of your hypothesis, the hypothesis is going to look like this. This x naught, x1, all these are representing your different set of the features. So now the parameter is going to be this one. Instead of having 1 or 2, here basically you need to devise the value for these set of the parameters. Cost function is going to be the same. The only difference is in your previous case, the cost function was driven with your theta naught and theta 1. Now here in this case, the cost function are going to be driven with respect to your theta naught till your theta k. Theta k is basically representing the total number. This k part is representing the number of the parameters which you are having. So it's going to be basically k plus 1 number of the parameters here. So you need to adjust all these parameters, and based upon that adjustment, you are going to have the different placement, and as you are having the different placement, your predicted value are going to basically you are going to have the different predicted. Okay. Now one of the approach which we have seen for deriving the value of your cost to deriving the value of your thetas. Now, there is another approach with which we can also work to derive the value of the theta, and that is your gradient descent. Gradient descent, basically, it is an optimization algorithm which is used which can be used for deriving the value of your theta naught and theta 1, or even more than that. Like here in this case, we are having k plus 1 features, k plus 1 parameters. So we can use this gradient descent in order to derive the value of k plus 1 parameters. And once you are able to derive the value, you can place it here. Once you are able to place it, and if you are satisfied with the performance, I can use it for I can deploy that model for the prediction. Now let's see how we can derive the value of your thetas based upon your gradient descent. So again, I will be explaining with respect to your with respect to a simple, that you can easily extend it with respect to your multiple one. So here I'm going to move on to your this simple one. Okay. So in this case, this gradient descent, as I mentioned, this is an optimization algorithm, and this optimization algorithm we will be using in order to find the parameter of the coefficient. Okay, that means the value of your theta, and that is to be driven with the minimization of your cost function. So here in this case, how it is going to work? So basically, we will be starting with at what location, what is my current location. Based upon that current location, I will be adjusting the value of my parameter, like the things which we have covered in your in your first session. Like suppose if I'm starting at this location, my minimum is this. So if I'm at this location, so in order to reach to this location, I have to do the increment, decrement. Suppose at this location you are present, in order to reach to this location, what I need to do is I need to perform the increment. So that way, this gradient descent algorithm is to work. It is going to do the either increment in my value or a decrement in my value based upon what is my current location. So in order to start this process, first I have to start with some random selection. So that's why here it has been written. First, you need to start with the random selection of your theta naught and theta. And over the number of the iteration, you are going to adjust the value of your theta naught and theta 1. Again, the same thing is based upon what is your current position. Based upon that position, you will be doing the adjustment. So, but yes, at your first phase, you will be starting with some random location, because initially we don't know what should be the correct position. So initially we will be starting with some random position, but yes, over the number of the time, we will be doing the adjustment based upon what is my current position, whether it could be an increment or it could be a decrement. So how we are going to do the adjustment? So that formula we have already covered, how we can, based upon the location, how we can increment it or how we can decrement. So basically this is representing that particular scenario. So if you're at this location, so I have to perform the increment, and if you're at this location, I have to perform my decrement. And this step means in what way you are going to proceed further. This is going to be driven with this is going to be driven with this alpha. This alpha is basically representing with what amount you are going to take that. Like if you are at this location and I found some value, like suppose I have found this 10. So how much this, in order to, means when you are going to make this move, how much effect this 10 should have on this calculated. So that is going to be basically tuned based upon this alpha. If you are selecting to a very large value, you are going to have a very long jump. And if it is a very small value, you are going to take a very tiny or very small step in order to reach to this. Advantage is going to be you will be able to reach to the minimum location, but yes, the disadvantage is going to be it's going to take lots of iteration to reach from this particular location to the final. That will be the disadvantage. Okay. So this step we have to do it with respect to theta naught also, because you need to derive the value of your theta naught. And this step you also repeat it with respect to theta 1 also. So as it is your, like from here you can relate it. As I said, you will be doing the adjustment in your theta, in your coefficient till your defined criteria, till your termination criteria. So in your one case where we were just doing the calculation and we are done. Here in this case, you will be doing this iterative process. You are going to repeat this process over the number of the times, and during that iterative process, you will be adjusting, and that with that adjustment, there will be a change in the placement of the line. As there is a change in the placement of the line, the cost function is going to be affected. And as based upon the cost function, we can basically make the decision whether to increase it or whether to decrease. So like here, what we were doing based upon, like, this is the case. Means when it is a positive one, then what means when you are getting the derivative as a negative, perform the addition. When you are getting the derivative as a positive, perform the decrement. And when the derivative is 0, so that means no further change is required. Okay. So here the linear regression, this is the equation for your model. This is the cost function which are going to be associated with it. And here what we have done, we have just merged this linear regression, and the whole process is going to be the same. The only difference is the way you are calculating with it. That will be different. So this is a linear regression with gradient descent. Same process you can do it, or same calculation we can do it with your multiple also. Like here in this case, till what point we are running it? We are running it till 0 and 1. Means we are just calculating the value for your theta naught and theta 1. In case of a multiple, it's going to be k. Means you will be calculating the derivative with respect to theta naught also, 1 also, till your k. That way you will be doing the adjustment. Okay, one more important point is, which has been asked, like it could be a case, instead of having just one global optimum position, it could be a case we are going to have the multiple local position we are having. So in that case, reaching to your global one, that will be quite difficult. It is going to be driven with what point you are going to start. Like here in this case, suppose if you are starting with this location, possibly you are going to converge at this. Suppose if you are starting with this location, I might converge to this one. Suppose if I'm starting with this location, so I might converge to this location. So that will be the case when you are having the multiple local position. But if it is one, then definitely you are going to converge subjected to what alpha you have taken, or what learning rate you have. Based upon that, you are going to converge. Like this is the case representing, if I am starting with the different location, so possibly I am going to converge at the different location. It is not all the time I will be converging to the same location. So the selection of the initial point is also going to matter in this particular case, if you are having this kind of the behavior. So in that case, the convergence is going to be driven with your the initial selection is also going to impact the convergence. Now this is the another part of it, how you can do the adjustment. So basically, when you are going to use this optimization algorithm, that too here we are using the gradient descent. So there are 3 ways to do the adjustment. Like in all the cases, whether it's your stochastic or your batch or your mini batch, in all these cases, basically we are going to adjust the we are going to basically calculate the value of your coefficient, like the thetas we are going to calculate. But when you are going to calculate this theta, means when you are going to calculate the cost, and based upon that cost, you are going to do the adjustment. So how many instances you are going to cover, that might be different. And based upon that, you are having 3 ways to do this. So like first one is your stochastic. So basically in case of the stochastic, you are just going to take one random sample. Based upon that random sample, you are going to calculate the error, and based upon that, you are going to do the adjustment. So instead of using the whole instance in order to summarize your cost, I will be just using your one instance. Randomly, we are going to pick one instance, and based upon that, we are going to make the decision. So that is your stochastic gradient descent. Coming to your batch one, in case of a batch one, we are going to use the all instances in every step of your gradient descent. Like the example which we have covered till this point, whatever things which we have covered, that is basically come under your batch, because in order to do the calculation, I am using, or we have covered all the instances, right? Now, the advantage, we are having advantage and disadvantage with respect to each of the aspects. So like suppose if you consider the stochastic, it is going to be very quick, because just one instance we are using, and based upon that one instance we are going to you are going to basically make the decision. So just one instance is there. In case of your batch gradient, you are going to use the complete instance. So the time requirement for your batch is going to be large compared to your stochastic. But if we talk about the performance, so this stochastic is just the random selection. Based upon this random selection, you are going to make the decision. But in case of a batch, we are using the knowledge of all your instances, and based upon that, we are going to make the decision. So that is going to be more accurate than the stochastic. But yes, it is going to take that time. So in between, we are having the another approach, that is the mini batch gradient. So in case of your mini batch gradient, here we are not ignoring all your instances. Along with that, we are also not considering all the instances. In between, we are going to consider some batches. We are going to make some batches, and based upon that batches only we are going to go. That means it is these selected batches are not containing all your instances. But yes, it is not ignoring the complete set of the information which is present in your training instances, right? So it is the balance between your, it is the midway, it is going to work. It is that you can treat it as in the midway approach from your stochastic and your batch, means batch gradient. So hopefully this part is also clear to everyone, what is this batch gradient and this means stochastic batch and mini batch gradient. Yes, yes, whenever we are working with the, whenever we are going to work with the, whenever we are going to work with the numerical values, right? And in the numerical values, basically, it could be a case your data, all the features is not going to lie within a same range. That could be, that is very much possible. So if this is the case, in that case, you need to normalize, you need to basically normalize your data, so that it should not be the case. When you are going to make the decision, your decision is basically going to be driven with your one feature. If this is the case, so your model which you have prepared, that is not going to be very correct one, because the model which you have prepared, this is driven with your one feature. So when you are having a very variety, or when you are having a very large scale gap between your features value, it's better to normalize the value, and then you can go with the then you can proceed further. Here I haven't done any kind of the normalization. We were having very small value. Just here I have used the small value to explain it, how we can use the, how we can basically implement your regression model to achieve our task. But yes, in your case, you have to analyze, like in my case also, we were not having any missing value, we were not having any outlier. But when you are going to do it in your experiment, means when you are going to do your research work, so you have to do the analysis of your data. So we are having one session related to how we can do the exploratory analysis of your data. So in that class, you will be able to understand how to analyze, means how to basically process your data, how to analyze your data. So that part we will be covering. That for that we are having a particular session. Okay, so hopefully till this part it is clear to everyone. And this is also clear to everyone how we can means implement all these model in your Python. So how we can basically calculate, how we can basically build your regression. Hopefully all these parts are clear to everyone. So if you're having any doubts, so that we can take it. So yes, one, okay, let's see for your, means here what we have done is we have just cover your linear regression using your means simple linear regression we have covered. Now if you are having the multiple features also, so the same code you can use it for the multiple features also. Like suppose it means no more changes required, means here I can, like suppose in this case I am just having the one feature. So if you extend it further, you can use it for the like suppose instead of having just, if I am having 10 features, so I can use these 10 set of the lines in order to make it for your this means multiple features. So whatever concept we Okay, so whatever concept we have covered, so that you can easily extend for your multiple regression. So for now, we are going to end it here. So if you're having any particular query, so that you can ask. So hopefully this multiple means how you can implement it your model in your by using your sklearn. So hopefully that part is clear to everyone, and the theoretical thing also. So just means what you can do is the way we have done it for your simple, that means for your one feature, the way we have used or the way we have written your code for the simple linear regression, the same you can use it for the multiple. Just replace your data reading part with the file